So today we're going to continue on with thermodynamics. So today we're going to talk about the first and second laws of thermodynamics. So the first law, like everything else that we've talked about this school year, this is also conserved. Remember, conserved means the total amount stays constant. So in any process, the total energy of the universe remains constant. That means that for any thermodynamic cycle, the sum of the net heat supplied to the system and the net work done by the system is equal to zero. Okay, what comes in goes out. So the first law of thermodynamics can be expressed mathematically by the change of energy equals the heat minus the work. Heat minus work. The change in the system's internal energy, remember that's delta U, equals the heat transferred to or from the system as heat minus the energy transferred to or from the system as work. So all the terms, delta U, the change in internal energy, Q and W are all in joules. Q is positive for the energy added to the system, negative for energy released from the system. Work is positive for work done by the system and negative for work done on the system. Excuse me. Okay, here's a chart that you can refer to for the signs of heat and work for a system. Okay, so if Q is greater than zero, energy is added to the system, meaning it's positive. Q less than zero, its energy is being removed from the system as heat. Okay. Q equals zero, no transfer of energy. The heat is the same. There's no transfer from warm to cold, remember? And work done by the system, if it's positive, work done on the system if it's negative. And if W equals zero, no work is done. Okay, if you remember our types of processes, and please pay close attention to this chart because this will be on the test, which is next week. So, in an isovolumetric reaction or process, there is no change in volume. So if there's no change in volume, no work is done. Okay. Excuse me. Isothermal. There's no change in temperature and internal energy. So your delta U, your internal energy, will equal zero. That means if you take your heat and you take work, subtract the two, you should get zero. Adiabatic, no energy is transferred as heat. So Q will equal zero. And an isolated system, don't worry about that. But remember, isovolumetric, isothermal, adiabatic. So, processes. The change in internal energy of a system is zero in a cyclic process. Okay, what do we mean by cyclic? We'll get to that in a minute. So, delta U, the net change of internal energy will equal zero. That means that the net heat, and the net work will both be equal. Okay, a cyclic process, a thermodynamic process in which a system returns to the same conditions from which it started. We're going to talk about it in a minute. A good example is a refrigerator or an engine. So, refrigerators, like the one in your house, use mechanical work to create a temperature difference and a transfer of heat. Because remember, when there's a difference in temperature, energy or heat will flow from the warm side to the cool side. Also, Heat engines use heat to do work. Hot gases push against a piston in the internal combustion engine. So, here is a typical process for the refrigerator. Here we have the Freon, okay? The compressor pushes the Freon through inside the refrigerator, okay? This is super, super cold. It's Freon gas. So it's going to absorb the heat from inside, from around your food. So it's going to absorb the heat. So now it's not as cold, okay? When it gets to the evaporator, it's exchanging the heat. Okay, then it comes to the coils on the backside, on the outside of the refrigerator. I'm sure you've all seen the backside of a refrigerator. So there's a valve here. Outside the refrigerator, this heat is given off and it's cooled off. Okay, so the condenser is exchanging the heat back. So the heat is going to the outside of the refrigerator, and the cooler is on this side. So the neon gas, the Freon gas is cooled off again. So heat is absorbed on this side. Heat is given off by the Freon on the back side. So if you ever put your hand near the back of the refrigerator, it's warm back there because it's moving the heat from inside to the outside. And it's all being done by a difference in temperature. The heat is going towards the cold, and then on the back side, it's giving off the heat, and it's being cooled off. Okay. An internal energy, the internal combustion engine, okay? In the same way, we have a spark plug that ignites the gas inside the piston. So when that ignites, it expands the gases. The gases heat up inside the combustion, and it pushes the piston down, okay? When it pushes the piston down, it causes this crank to move. So, there we go. After it's moved, a valve opens in the cylinder and the gases can escape. So the piston will go back up. Okay. Exhaust valve closes. The intake valve opens, puts more air back into the engine. Okay. Fuel gets pumped in. And then, sorry about that, guys, the spark plug sparks again, and it causes it to ignite and push back down. So you have fills with gas, ignites, pushes the piston down, okay? And then it releases that, and the piston can come back up. And then it ignites again, and it comes back down. And this up and down cycle is moving this crankshaft. Very sensitive mouth, sorry about that. So that's how we have a cycle of the compression, the ignition, the expansion, and it goes round and around. Okay, second law. In an ideal cyclic process, internal energy is conserved. That sounds kind of the same, but in this case, the net amount of work is equal to the net heat flow. Okay, so QH is the heat absorbed by the engine, the heat engine, or the refrigerator. QC is the heat given up to the surroundings. So the net amount of work is going to equal the net amount of heat transfer. So this would be the back side of the refrigerator minus the heat of inside the refrigerator. Okay. The difference between the two is your net heat exchange. That net heat exchange is equal to your net work. So based on this, a heat engine could do more work on a hot day than it could do on a cold day, and could always perform as long as the engine's temperature was less than the surrounding air temperature. Okay? This situation never happens, but in theory. The second law of thermodynamics: no cyclic process that converts heat entirely to work is possible. There is no 100% efficient cyclic process. Okay? Like there's no perfect world. Well, there's no perfect cyclic process. Close, but there's always a little that escapes. Some energy must be transferred to the surroundings as heat. So, in any process, you're never going to reach 100% efficiency. And so, efficiency, don't panic. I am not going to have you calculate efficiency on the test, but I do want you to know the efficiency is the rating on how well the engine works. What percentage of heat absorbed is converted to useful work? Okay. It will never be 100%. We're not that good. But the efficiency is the percentage, again, of heat absorbed versus the amount of work done. Okay, kind of in layman's terms, what are the different laws? The zeroth law, which we covered 1 and 2 today. You must play the game, meaning two systems that are in thermal equilibrium with the third system are also in thermal equilibrium with each other. So if A is equal to C and B is equal to C, then A and B must also be equal. Okay? First law, you can't win, you can only break even. The total amount of mass and energy in the universe is constant. It's conserved. Second, you can't break even. That means there is no 100% efficient thermodynamic system. The entropy of the universe is always increasing. Entropy can be the disorder. Okay. And number 3, or the third one, you can't quit the game. We talked about absolute zero is not possible. Absolute zero is the part where the particles are so cold that there is absolutely no movement. There's no internal energy within a substance. We've come close, but we've never been able to achieve absolute zero. Okay, in general, the laws of nature are allowed to act without interference. A disorderly arrangement is more likely to result than an orderly one. That's entropy. Entropy, think of it as disorder. So entropy, when you hear that word, is the measure of a system's disorder. Okay? Systems with maximum disorder are favored, meaning they're more likely to happen. Once a system has reached a state of greatest disorder, it will tend to remain in that state and have maximum entropy. Okay, I wanted you to be familiar with the word entropy. Okay. Increasing disorder reduces the energy available for work. If all the gas particles in an engine were moving towards the piston, more work can be done than the random motion of the particles, let's say. Solids are more ordered than liquids. Liquids are more ordered than gases. Just think about where all the particles are going. In a solid, they're in an orderly arrangement. In like water, a liquid, they're moving around, okay? But in a gas, they're all over the place. Local decreases in entropy must be offset by increases somewhere in the universe. It just means as something gets more disorderly, something will get more orderly. So, what does this mean? This is more theoretical, but they say that the universe will eventually settle into a state of thermal equilibrium and reach maximum entropy. What does that mean? So remember, heat transfer, if heat is being transferred, meaning work is being done, what's going to happen when everything in the universe is exactly the same temperature as everything else? There will be no heat transfer and there'll be no work. The transfer of heat and the ability to do work will be impossible. All physical, biological, and chemical process in the universe will stop. Now, this is known as the death of a universe, and it's projected to happen in 100 trillion years. I don't think you or your children or your children's children need to think about that. But on the theoretical event, that is the death of the universe. And that is it. Ending on a really positive note. Okay, get these in your journal and get them to me. A reminder, you will probably have a test early next week. Talk to you later.